end of additional data if people ask questions or you want to know something about that. So I think we should form our ideas around data. And I'll tell you, I jumped into this subject because about, I'm guessing Lane can correct me, maybe 15 years ago, original company I started, Pinnacle Technologies, we got approached by the national labs to monitor CO2 sequestration. So getting CO2 out of the air and injecting it deep underground, like produced water disposal. And it had the prospect to become a big business line for us. In fact, it did become a business line, a profit center at Pinnacle. But I got wondered, why is this really a reasonable thing to do? With the expense of doing that, is that a good trade-off? Just a curious guy. So that got me interested in trying to understand this whole issue of climate change. What is the basis of the issue? What is the data? How has the data evolved with time? What's the true story on it? The other reason I got brought into it was when I was in high school in Colorado here, so in the early 80s. There was a different sort of mania then, which is that we were running out of everything. You're going to have mass starvation by the year 2000, running out of oil, gas, tin, copper, iron. We had this impending resource crisis. And as a high school kid, oh God, I was taken in by it. Part of the reason I went to MIT was to work on fusion energy. Because if we're running out of oil and gas soon, I want to be part of the future of energy. And I believed it then because everyone believed it. All our teachers, we had a CU professor who came and talked on it. And that I got swept up by what I call the argument from authority. People think something's true because everyone says it's so. And of course, I think everybody in this room and in Liberty knows that isn't the case. But this is one of those ones that just because everyone says something, that's not enough. Dive in, take a look at the data. So first talk I gave on this was to elementary school and junior high school. I gave one at a University of North Carolina 2 months ago, and I've given them in Denver a few times. But I just love the topic. There's a bunch of data on it. There's some cool chemistry and physics behind it, and then there's this, and then ultimately it's a sort of a social, political trade-offs. But the start of anything, before you form views, it's always got to be based upon what? Based upon data. So since the issue of climate change, and again, jumping to the end, when I talk to kids or even universities, I rarely give my opinions. Among friends or among family here, I'm going to show data and tell you exactly what I think of it. But often I don't do that because I don't want to be like the other side and go in and try to convince you of my opinion. I just want to show people data. Here I'm gonna liberally mix the two. But ultimately this issue is about energy. Climate change affects one industry, it's about the energy industry, and it's about where we get energy. And again, there's a lot of views on that. So the first thing is let's look at that actual data. Well, this only goes to when I was in junior high, but if you go back, to when I was born, the industry we're in, oil and natural gas, provides 63% of the US energy in 1980. It actually provides 64% of the energy today. And by the US Energy Information Agency, so just a government agency that tries to extrapolate trends and prices, by their estimate it'll be 62% in 2040. So where energy comes from, it doesn't change fast. You hear all these, we're going to be all renewable by 10 years or 20 years. Even if those technologies were as great as everyone said, even if we continued to pour trillions of dollars in subsidy of them, that will not happen. The changing of energy systems, which power everything in the world, is a slow, transformative process, has been in the past. It took a long time for coal to displace trees, grass, wood. Essentially, we were 100% biomass throughout all of human history until about 200 years ago when coal burst on the scene. But it was a slow process for coal to become a dominant supplier. Oil came later, gas came second. So the other big suppliers are coal. If you add oil, natural gas, and coal together, hydrocarbons, they're a little over 80% of energy in the world. When I was born, they're a little bit over 80% of energy today, and they'll probably be about 80% of energy when I die. So there's a lot of technologies and dynamics going on within that, But this belief that sort of one source goes and displaces another quickly, it has not happened in the past. It's extremely unlikely to happen today. And it's not just, there's a transition time that's slow. So if the economics were compelling or whatever reasons were compelling somewhere else, you could have the start of a transition, but it would happen slowly. Today, there isn't really a driver of any transition to begin with, except within hydrocarbons. Natural gas is displacing oil a little bit. Natural gas is displacing coal. Renewables, again, maybe 7% when I was in junior high. They're 8% today. By our government's projections, they'll be 10% in 2040. The number one source of renewable in that is hydroelectric. The number two source is biomass, not modern biofuels, just biomass, burning grass, trees, sticks. And wind and solar today are like 2% of US energy. And by sort of estimates, they might be 4% in they might be worldwide 4% in 2040. They might be 5 or 6% in the US. But that's assuming large continued subsidies and growth and all that. So that's the future, but I just want to show the data of where do we get energy today. Here's another plot relevant to the climate change. This is not my climate change talk, it's just giving some background comments on energy. So here is the percent of the energy we get from carbon-free sources. So carbon-free means not hydrocarbons or biomass. That's included in that. So again, when I was in college, it was 13%, and today it's 13.5%. It hasn't moved much. It used to be lower before the arrival of nuclear, right? This was just hydro as the main non-carbon-based energy source. Nuclear power came, rose up, and by maybe 1990, it was 13%, and it's been pretty flat. In spite of $1.3 trillion of subsidies, the amount of energy we get from non-carbon-based sources hasn't moved much. The prospect of it moving a lot isn't very great either. One last picture on energy before we get into climate change data. This is a Google Maps photos, 2 different Google Maps photos from the same border. But that's a national border right there. Turns out the left, that's Haiti, and that's the Dominican Republic. So one has a lush rainforest throughout most of the country, and one is almost entirely deforested. Why the difference? Well, the Dominican Republic has oil and gas, and therefore they get their energy from that. They're a wealthier country and they use hydrocarbons. Haiti, through not through geography or anything, through bad governance, is so poor they don't have much oil and gas, so they get their power the same way our ancestors got their power, which is burning trees. So even if you don't have a modern economy, food, when we grow grains, they're complex carbohydrates that our digestive systems don't break down very well. So even our ancestor 10,000 years ago, they needed to cook food to break down those molecules, those carbohydrates, so they could digest them. So we cook food, and that is burning sticks, grass, dung. So that's what our ancestors did. That's why England is totally deforested, because coal did not arrive in time. Western Europe has lost a lot, but has most of their forests because coal arrived in time. If you don't have modern hydrocarbons, you eventually, if your population grows at all, you will deforest yourself as Haiti did. All right, now climate change. I'm going to give a quick summary of what we do know in big picture stuff, and then I'll go through the detailed data. So is the climate changing? Absolutely. And of course it always has. It's a dynamic system. Has the Earth warmed over the last 160 years? And the reason we say 160 years is we only have reasonable global temperature measurement instrumentation coverage over 160 years. Since about 1850, 1860. So has the Earth warmed? Absolutely. It's warmed by a little less than 1 degree C, 0.9 degrees in 160 years. Does increased CO2 in the atmosphere contribute to global warming? Absolutely. CO2, and I'll talk a little bit more about this, absorbs long-wave infrared radiation. So some of that radiation absorbed and re-emitted and is scattered into space, but some of it is radiated back down to the surface of the Earth, so it produces a net warming effect. Hence the name greenhouse gas. has burning of hydrocarbons been the main driver of increased CO2 concentrations in the atmosphere? Absolutely. Pre-industrial times, 200 years ago, even 170 years ago, we had roughly 280 parts per million, so 0.028% of the atmosphere was CO2. We've risen it now to about 400 parts per million, or 0.04% of our atmosphere is CO2. How much, so if you extrapolate the current trends, we burn lots of hydrocarbons and we continue to grow the CO2 in the atmosphere, actually we won't get, by almost any methods, we won't get to a doubling from that 280 in pre-industrial times, but we might get close to a doubling by the year 2100. So 84 years from now, we might roughly double the CO2 concentration in the atmosphere. So by basic physics, how much will that warm the atmosphere? So about 1.3 degrees, 0.9 of which has already happened. So if there's no feedback, we'll get of order a half a degree more warming from now to the year 2100. In the absence of feedbacks, and of course in all dynamic systems, is the feedback positive, negative, no feedback? So these basics are not controversial. The scientists in the IPCC, those that are advocates for climate change legislation, all that, no one in the media and government confuse this stuff all the time. But the actual scientists, these are not controversial facts. This is the generally accepted stuff. The question is feedback. The models, the whole sort of basis is, well, there could be this big positive feedback, and maybe we won't get a little over 1 degree of warming, maybe we'll get 3 or 4 or 5 degrees of warming. So jumping to a conclusion, let's just talk about, so the real question, maybe everybody's here and we're going to look at this data about, is should we take action on climate change? Should that be something we should all worry about? Should Liberty try to figure out how we can reduce our greenhouse gas emissions? And there could be a case for that, absolutely. But you need 5 facts to be true for it to be logical to take action. Number 1 is there has to be positive feedback. If there isn't positive feedback, it's just the straight physics of CO2 absorbing infrared radiation, and re-radiating it back, and we end out that from the year 1850 to the year 2100, the world's 1.3 degrees warmer. Is that a bad thing? From an economists are looking at it, it's almost uncontroversially a positive thing. A little bit, far more people die from the cold than die from the heat, even in Greece. Agricultural productivity goes up with the modest warming. If you look historically, if it's colder by a degree or 2, it's worse for humans. A little bit warmer, that's positive. So this, again, even among advocates in this field, sort of uncontroversial, that would be a positive for the world. Nobody would be alarmed about that. So you have to have positive feedback to even have this issue worth talking about. So if we had positive feedback and say the temperature warmed 3, 4, or 5 degrees, the IPCC, the Intergovernmental Panel on Climate Change, they lower a little bit their projected temperature rise, but if you take the upper end, 3, 4, 5 degrees, we should take action if there's amplification, and if that 3 or 4 or 5 degrees has real negative impacts on the planet. It might. This one I think's got a reasonable chance that one's true. Then, given both those, you still need to believe that we could pass policies that would meaningfully reduce our CO2 emissions. The record to date on that's not so good, but you never know. You'd have to believe that those policies would be spread. The CO2 is mixed very well in the atmosphere. So to reduce CO2 emissions, what you do doesn't matter. It's what the whole world does. So you'd have to believe there are policies to reduce them, and that they'll be implemented by at least all the major emitters of CO2. And then number 5, you'd have to believe that the cost of these policies, you're going to invest some money, that the return on them would be at least comparable with other issues. Indoor air pollution, which means people that don't have oil and gas and burn sticks, grass, and dung in their huts. About 4 million people a year die from that. Particulate pollution, clean water, malaria abatement, poverty, hunger abatement. So to make sense to act, you have to believe in all 5 of these. This one I think might be true. Myself, the other 4, and none of the other 4 look likely. So to me, the odds of all 5 being true, probably not so great. But everyone should form their own opinions on those things. So let's go back, into the data. So I'll keep this section super short. the chemistry. Where does CO2 come from? So the simplest hydrocarbon is methane, right? It's one carbon molecule and 4 hydrogens. It's the primary component of natural gas. So to combust something means you chemically combine it with oxygen. One methane molecule plus 2 oxygen molecules creates 1 CO2 molecule and 2 water vapor molecules, 2 water molecules. So when you see all those pictures, usually on those posters, you know, those big white clouds coming up from power plants, CO2 is transparent. That's water vapor. Now in the old days, when I was a kid, you know, they were grayish or brownish big clouds coming out because there was you're burning coal, they're particulates, they didn't have scrubbers, they're dirty. If it doesn't have any color, all those big white plumes you see, that's water, right? So we don't worry too much about water vapor. CO2 is the one that, as they say, absorbs infrared radiation, and in the atmosphere, it'll lead to a slight warming of the planet. The other thing to keep in mind, this is often called a pollutant now. So water and CO2 are essentially the 2 most important chemicals for life on Earth. You cannot have life, the life we have, without liquid water. The carbon source, we are all life on Earth is carbon-based. The source of carbon in plants of all kinds, including the ones we eat, is CO2. They get that from the atmosphere. So you can't have life on Earth without water vapor and CO2. So I have trouble with calling this a pollutant. It's not like mercury, it's not like NOx or SOx. It is essential to human life. We can argue about how much we should have, but it is not a pollutant. So this is maybe super techy. So when we think of something's hot, right? How does something cool? It either cools by conduction of heat. This table's colder than my hand, so when I touch it, I'm warming the table and it's cooling my hand because heat is flowing from my warm hand into that table. And then there's convection. We walk outside and that cold air, it conducts heat on us, but that's pretty slow. When it blows by us, we're warming the air and it's moving and cold air is arriving and it's taking away heat. That's convection. So on the Earth, most heat is transferred by conduction or convection. Now for planet Earth, that doesn't work very well because there's no wind blowing by. Space is empty. There's nothing Earth is touching. So it can't lose heat by conduction or convection. So the other way you transfer heat is what's called black body radiation. These are how those cool night vision goggles work for the soldiers. So if you're anybody, a human being, we're a certain temperature and we are radiating away long wave radiation, infrared radiation, and the wavelength of that depends on our temperature. So those infrared goggles tell that, hey, human bodies are different temperatures than rocks and trees and trucks, and they can sense that infrared radiation your body is radiating. So that's the only way the Earth loses heat. We get all our heat from the sun, or 99.9%. We get another 0.1% from radioactive elements decomposing within the Earth. That's the source of geothermal. That's why it's hot down in the Earth. But most of our energy comes from the sun. So the surface of the sun's a little over 5,000 degrees Kelvin. So that means the wavelength at which it radiates heat is centered around about, call it 6,000 angstroms, 600 nanometers. And by no coincidence, our eyes are tuned to see in that range at which the sun is sending radiation to the Earth. So that's short wavelength, high energy, because the surface of the sun is hot. Now, the Earth isn't nearly as hot. It absorbs that. And then the Earth, the only way the Earth, it just keeps gaining heat from the sun. If it couldn't lose heat, the temperature of the Earth would just keep rising and rising until it got to 5,500 degrees. But we lose heat by that long wave infrared radiation. So it's at a much lower wavelength, much lower temperature of the energy. So this is how the Earth is trying to release its heat over this sort of scattered spectrum. Now all the long wave stuff is absorbed by water vapor. There's lots of water vapor in the atmosphere, far more than CO2. It is by far and away the dominant greenhouse gas is water vapor. But it has a spectrum in which it's not very good at absorbing. So that's the wavelength of this black body radiation. That's how we actually lose heat, the stuff that doesn't get caught by water vapor. Now CO2 has a different absorption spectrum. The longer wavelength, I mean the lower temperature stuff, CO2 traps a narrow band, That's how it causes warming. Some of the stuff that water vapor lets through gets caught by CO2. Oxygen, ozone, and methane, and nitrous oxide, they absorb some higher energy, shorter wavelength infrared radiation, so they also block and get some greenhouse effect. We could talk about this for an hour and a half, so enough on that. Everyone gets CO2 adds some warming, water vapor adds much more warming, methane and ozone get a little bit. So climate change, big picture. Before I go into measured data, I'm going to talk about what we know geologically. And it's really just chemical composition of rocks and it's air bubbles. There's two different main isotopes of oxygen. They have different weight. So when it's hot out, those little air bubbles they get in the Arctic ice cores, Antarctic ice cores, there's a different ratio of oxygen 16 and oxygen 18, depending upon what temperature the air was. So they're not as good as thermometers, but we have some imperfect proxies to see what was the Earth like before. And we all know from Jurassic Park, and of course from science, that in the time of the dinosaurs, the Earth was dramatically warmer, wetter, lusher, greener, a lot more biologic matter alive than it is today. So when the Earth is, and of course it was very CO2 rich, so the planet was all like a jungle. We have a lot of dry, relatively sparse vegetation. We've had at least 3 times when the entire Earth froze. So the ocean at the equator was frozen. I would say it's a very unique thing. Water, almost any substance, it's least dense as a gas, gets more dense as it becomes a liquid, and it gets more dense still when it becomes a solid. We're crazy lucky that water is weird. Water is less dense as a liquid, becomes more dense as a liquid, and then less dense when it freezes, right? Our ice cubes float. So when the Earth froze over, the surface of the ocean froze, and it becomes insulating. So that ice got thicker and thicker, but it never got anywhere near to the bottom of the ocean. If water froze and sunk, it would have frozen the whole oceans. We would have ended life on the surface of the Earth. So thank God water expands when it freezes. So this is a geologic record. So this is just looking at, in certain rocks, things. So this is very rough. This is not like a temperature measurement. But blue is a proxy for temperature in the historical time. Green is CO2 concentration. Purple, yeah, purple is CO2 concentration. And this is 500 million years. So roughly the time at which life left the oceans and we had life on land. So this is very long, and it's also sort of the time period in which oil and gas was created. So we're way over here in the modern era. So 2 things you can see. We live in a rather cold and rather CO2 deprived time. The average CO2 concentration in the atmosphere was probably a few thousand parts per million. We're only at 400 today. We were at 280 before. At about 150 parts per million, photosynthesis starts to shut down. If air concentration, CO2 concentration got down to 100 or 120 parts per million, the Earth would slowly die. Plants can't grow, photosynthesis doesn't work, things go bad. Al Gore used this data, and it's really cool data from these ice cores in Antarctica. So that was 500 million years, kind of a rough geologic record. This is 400,000 years. So this is going to Antarctica, drilling with our technology, a deep hole, pulling out these ice cores, 2-mile thick ice cores, and you cut each one of these layers, and there's little oxygen bubbles, and little air bubbles. You can see what's the CO2 concentration in that air bubble, and what's the ratio of oxygen, so that tells you CO2 concentration, and how much oxygen 18 is there compared to oxygen 16, and we can tell what temperature the air was when that bubble was entrapped. So you get this cool proxy of last 400,000 years. What is the temperature been, and what is the CO2 been? So we are here. Humans have developed agriculture and writing and modern civilization all here. Here's blue, much colder. Little warm spell, very, very cold, brief warm spell, very cold, brief warm spell. So we are in the middle of an ice age, and we have been for about 2 million years. So the Earth has been in this crazy cold time where we have ice age, even in these warm interglacial periods. We still have frozen ice on the Arctic. We still have a giant ice mass on Antarctica. We have glaciers. That's very, very rare in the history of Earth. So we're in an ice age. The lucky part is we are right now in the interglacial period, these warm interglacial periods where the ice recedes, it's only on the poles, it's warmer, and plants grow, and life is better. These interglacials last 10 to 20,000 years. We're about 15,000 years into it. So, and the reason for this cycle, we believe, is this wobble in the Earth's orbit and the wobble in the Earth's tilt with respect to vertical. A Serbian guy, Milankovic, came up with, how do you explain this crazy pattern we've been in recently? So it's roughly 100,000 years. So 100,000 years ago, they called this the Emian warming. It was, well, can't use this, but it was warmer than it is today, significantly warmer than it was today. The polar bears did fine, and the Emian warming, there was not permanent ice at the North Pole and all that. So in any case, we're in this warm period. If you go back just 20,000 years ago, where my house is in Montana, most of the northern US was under a mile of ice. So people worry about the Yellowstone supervolcano. I'm like, it's probably in the next 50,000, 80,000 years. Within 10,000 years, very likely my house will be scraped off of the earth and buried under a mile of ice again. But it happens slowly, so we'll have plenty of time to migrate to. We'll have to go to Texas. I know Jim Brady won't like that, but Jim's descendants will eventually be Texans. Let me just leave it at that. The other point I'll say, so red is CO2 concentration. So Al Gore made great hay out of it. When it gets really, the CO2 concentration's warm, rises, the temperature gets really warm. When the CO2 goes low, it's really cold. And look, we've gotten this warm, but CO2 is not going to stop here. It's going way up there. We're all going to fry. Now, Al Gore, I think, knew, because the scientists certainly know, that in this data set, as you can probably see, the temperature rises first. That's because the change in these, and it's several hundred years later, when it gets warmer, the ocean's warm. Think of your soda can. You take a cold soda out of the refrigerator, you pop it open, and poof, not much happens. You take a warm soda can and you open it, and poof, you see the bubbles, it overflows and all that. Even if you don't shake it, you see lots of bubbles. And it's because water dissolves a lot of gas when it's cold, and it can't dissolve as much gas when it's warm. So as the oceans warmed up, they couldn't keep all the dissolved CO2 they had. They expelled it into the atmosphere. So everybody in the science world knows temperature drove the change, CO2 responded. What we are in is a very different thing. Temperature is wherever it is, and we are driving the CO2 change. So the response to a change in CO2, in temperature, is a very different question to when you just change temperature, what happens to CO2. I think Al Gore knew that, but it was a great story to tell and use cherry picker and all that. Quite dishonest, but nonetheless. So now we're going to get to the more clearer, the actually measured data, not inferred from rocks, not indirect, but just direct data. These cool things called thermometers that started with the fact that mercury expands or contracts based on temperature. So the oldest, every once in a while I want to give Mark Pearson credit, the oldest continuously operating temperature measuring device is in his homeland in central England. So they've had a temperature monitoring center at the same location in England for 350 years. So it's, it's great.
An American one actually back then. It was 100 years, before the Roman.
So in central England, so what you can see from this is, the biggest thing you can see is what we call weather. This year was cold and next year was warm. The variations there are dramatically bigger than maybe a degree of warming in those 350 years. So ironically, I think the second coldest December in the 350 years of this data set was 2010. But this is just cold year, warm year, cold year, warm year. So that sort of short-term variation totally swamps the trend. Not that the trend's not important, but we always view it as way bigger than it is. Everybody says, oh God, when I was a kid, it was so much colder and all this stuff. And I hear it all the time. But if I turned the temperature in this room by the same amount the world was colder in 1850, only a quarter of you would even know the temperature of the room had changed. And that's over 160 years. So this kind of, that kind of stuff, that's just sort of this self-reinforcing, meme going on. The world has warmed, but it's pretty small actually. So I plot this on a 0, the freezing, this is all centigrade, the temperature of science. So this is the temperature water freezes at. This is a warm summer day. Here's the average temperature of the globe over those 160 years. And of course, it's all about scales, right? Just a flat line, because it hasn't moved much. But if you zoom it up, here's the sum of the global temperature data. But I've done one thing different here, and I'll show it the normal way, is it's just averaged. It's average, so you get out of the wild variations and just average the temperature of the Earth. And my favorite line is the green one. So it's 120 months, so it's a 10-year running average of the average global temperature. Look at the scales, and this is a thing we just call different from the average. So the variance. So 0 degrees, so this from the bottom of this plot to the top of the plot is 1.2 degrees centigrade. So there was a slight cooling the end of the 19th century. We had a warming from 1910 to the 1940s. The Germans took a warship from Germany across the top of Russia to the Pacific Ocean. It was a relatively warm time. Then we had actually a slight cooling, not much, but it's hard to believe that maybe 1/10 of a degree of cooling globally averaged. Of course, you could find local places that it got 2 degrees colder. This set off the global cooling scare of the 1970s. And then we had a significant warming from sort of late 70s to about 2005. And this is the stuff that they said, and then it's going to get faster and faster and grow up. And then we've had about 15 years of plateaued temperatures in these last years. And the thing I look at is this one, before we burned a lot of hydrocarbons, before we changed CO2 emissions, doesn't look a lot different from that one. It's a little different, but not a lot. And then, so there's sort of these 30 or 40 year cycles, sort of flat, warming, flat. It's more complicated than I'm going to show here, but if you show an ocean cycle called the Pacific Decadal Oscillation, so it is basically where is the warm and the cold water in the Pacific. There's these very long-term ocean cycles. When the PDO is in its cool phase, the Earth temperature is flat, maybe slightly declining. When it's in a warm phase, we get a warming. Then it was in a cool phase. We had that warming, from late 70s to early 2000s, and now we've plateaued. And maybe it's all coincidence, but the Pacific Decadal Oscillation is back in its cool phase. And think of El Nino, right? We had a huge El Nino last year. It just ended maybe 6 months ago, 2015, 2016. And the simplest way to think of El Nino is the heat capacity of the ocean is about 1,000 times greater than the heat capacity of the atmosphere, right? It's hard to warm water with hot air, warm air, but you can easily warm air with a lot of hot water. There's just more heat capacity in water. So what the PDO warm phase means, heat is leaving the ocean and warming the atmosphere. And in the PDO cool phase, the heat flow is going the other way. The ocean is absorbing heat from the atmosphere. So if you take out that flip-flop, there's just a gradual warming going on, and it's being offset by this transfers between the ocean and the atmosphere. There's also an Atlantic there's a bunch of ocean cycles, but that's the simplest way to look at this. But this one you can see as well, cold year, warm year, there's huge short-term variations. The previous data I showed you, I just averaged it over a 10-year running filter or 5-year running filter to smooth it out so your eye could more easily see the trends. And this is the whole globe, so this is just averaged over the whole globe. More recently, and we average over the whole globe means all the temperature and thermometers that are all around. There's a lot more in the US and Western Europe than there is in Africa. We don't have very good stuff in the ocean, so these are imperfect for sure. But there's better statistics going on to get a better record. But things changed in the late 70s. Technology. There's now satellite networks orbiting the Earth. And these microwave sondes get a very good measurement of the temperature of the whole atmosphere. The upper atmosphere, the middle, they can break it down by slices, can break it down geographically, and we now have quite good measurement of world temperature data. You can't, the US temperature data, the ground data now is unfortunately by an organization tweaked constantly. They constantly make the recent temperatures warmer. And they're constantly adjusting the 1930s and say, yeah, it wasn't as warm as we thought it was. So there's a lot of, it's not that relevant to the dialogue, but this is the crazy politics of this thing, fudging with the data. Satellite data and these weather balloon data, there's no fudging. They're just sort of very clear measurements. So what you see is, here are the projections of global temperatures from the climate models. Now this is a hindcast. They would predict that we should have had just as rapid or more rapid warming in the past because it's a logarithmic function. As they said, we've increased CO2 by about 40%. That should be 2/3 of the temperature rise you get from a doubling because it's a logarithmic function, right? So if you put in a logarithmic function, you couldn't get anything to match anything. So they sort of have a story that, well, there used to be a lot of volcanoes and there's aerosols in the air, and then they're kind of magically balancing off most all of the heating. So we judge the aerosol factor and we sort of match the back data. But going forward, all this warming is really going to warm the planet. So here's their predictions that they've made of what temperature is going to do going forward. So really, this is sort of a measure, a model from here predicting forward. So and they run a whole bunch of different models, and they average the models together to get this red line. But that's the prediction. And the real data, Doc sees this sometimes, the real data has not cooperated at all with the predictions. In fact, the rate of warming in the models have been 3 to 4 times what the actual data has shown. And there's 2 data sets here. The circles, the green is balloons. They release balloons twice a day around the Earth to measure temperature of the atmosphere and profile. And then the other one, my favorite one, is just satellites. These are satellite radiosonde measurements that are constantly measuring the temperature of the atmosphere from the upper atmosphere all the way down to the ground. So it's also why when you read articles and you hear things about climate change and pronouncements of fear and destruction coming, they never talk about data, right? Because the data doesn't show it. The models show, my God, go out there. It's really going to be warm. But a model should look something like the data. That's been a problem. So why are the models so wrong? And I talked briefly about this before. And this is just my theory. A lot of people have the same theory. Most likely, I think it's clouds. The models are these big finite difference models, and they take blocks of the Earth, and they're generally blocks that are tens of kilometers on a side. So the whole Denver area is just one element in their model. In fact, a big chunk of Colorado is one element in a model. Clouds are micro-scale formation things, so they don't model clouds. You just put an assumption about clouds. Clouds will stay the same. We'll get more clouds. We'll get less clouds. It's just the most important variable by far and away is just assumed. So what happens is the idea of positive feedback, the theory for why this 1 point some degrees could turn into 3 or 4 or 5 is that, hey, when it gets warmer from the CO2, when the air is warmer, it can evaporate more water vapor. Warmer air is obviously for the same relative humidity has much more water vapor in it. So we can evaporate more water vapor, and water vapor is really a strong greenhouse gas. So that is going to increase the warming we would get from just CO2. So it's a reasonable premise, but the observed data doesn't show it. We've had a warming about consistent within no positive feedback. So they assume this large positive feedback that CO2 warms it, more water vapor, the water vapor stays resident in the air and causes maybe this increased warming. But perhaps the increased water vapor makes a wetter atmosphere, more clouds are formed, and it falls out as rain. You think of it in the tropics, where it's really humid and really warm, it rains a lot. So the study comes down to clouds, and there's a lot of work going on to clouds. And and I think even the IPCC, they've been lowering their temperature projection a little bit because we've not been able to find much positive feedback to really explain the story. It's also why the story has switched from temperature to extreme weather, and that's where we're going next. one other projection from the Intergovernmental Panel on Climate Change, I didn't explain too long. In 1990, their first assessment report, they not only projected temperature, but they projected methane. And as it warms up, the muskeg, the permafrost is going to release all this methane, and atmospheric methane is going to rise. And the yellow, they said somewhere from there to there. And then their second said, well, maybe it won't be as bad as we thought, and then it was from there to there, and then there to there, and then the last one, they ratcheted it down to here. But here's the real data. So not even in their 5 to 95% confidence bounds. In fact, it's never been within their 5 to 95% confidence bounds. So when you think, geez, over 25 years, you never once entered the 5 to 95% confidence bounds, maybe they're not right. That's just a thought. So let's talk about other things. I maybe spent way too long on temperature. Here's sea ice. We hear about this one all the time. The polar bears are going to die, the sea ice is melting, it's happening faster than we thought, it's going to be ice-free. So one thing that's curious is when they talk about ice, they only talk about the Arctic. And if you think about a circle, it has two poles, right? There's a north one and a south one. So I think the only way to look at sea ice is two poles. So if you add the sum of the Arctic and the Antarctic sea ice together, we've only had good satellite data since 1979, so this is the entire data set. And it goes up and down, and it goes up and down. It looks like the moon phases because it's the Arctic is freezing, but the Antarctic is melting, and you see that sort of dual phase. So that is the entire 35 years of sea ice data we have. Anybody see the rapid decline or the alarming disappearance of the ice? This is what's called the variance. So how different the ice is compared to normal, right? In 2004 we were up like 2 or 3% from normal. I think in 2005 we were down 2% from normal. But there's been no trend in sea ice. From what you hear in the news, can you believe that? That's the data. So this may explain part of it. And since we do have two poles, the Arctic sea ice has gone down, and the Antarctic sea ice has gone up. And if you go back historically, even over hundreds of thousands of years with these temperature proxies, they're out of sync. When the Arctic is warming, the Antarctic is cooling. The actual ice mass on Antarctica is growing. It's actually reducing sea level rise because it's growing. But the Arctic has definitely been warming and it's been shrinking. I don't know why the Arctic is warming and the Antarctic is cooling, but it's probably not scientific to talk just about one. We don't talk just about the cooling in Antarctica and the surge in Antarctic sea ice. Just talk about global sea ice, flat, in all the data we have. So what about sea level? The sea levels are rising. This is from tide gauges, so this is the way you can go back further. Reasonable, not great, but reasonable tide gauge data to about 1700. Sea level didn't move much, and then about 1850, a little bit after the end of the Little Ice Age. We had a very cold period when our founding fathers were here, Washington crossing the Delaware, sort of 1400s, 1500s, 1600s, sort of 1700s were cold. And then we've been, and before that, the medieval warm period. Remember, the Vikings settled Greenland and grew crops on Greenland around the year 1000. So the Earth does have a cyclical warming and cooling and all that. So a lot of our recent warming could be coming out of the Little Ice Age. But global sea level really started to rise about 1850. So we meaningfully moved atmosphere CO2 concentration by about 1950. So maybe it knew 100 years in advance you guys were going to drive SUVs and develop fracking technology and all that. But sea level's been rising for about 160 years, and the rate of rise hasn't moved that much. We always say it's faster and faster now. Well, I don't see the wild acceleration. I can believe there's been a modest acceleration. And this is tide gauge data, so the error here it's significant. So let's look at the really cool data. This is processed by the University of Colorado at Boulder. It's satellite data looking down and getting a global average sea level rise from satellites. So this system was put in place and running by about the very end of 1992. So we've got, again, about 25 years of sea level data. You guys see the big acceleration in sea level rise with the increasing CO2s? Yeah, I don't. But so sea level's been rising about, it's been rising about 3 millimeters a year. That's about a foot a century. And last century it rose maybe 9 inches. So maybe it's a little faster, but here, so that the head of NASA Goddard Institute of Space Science and the guy who did the famous testimony in the US Senate in 1988, Al Gore had James Hansen testify. This was sort of the start of the political movement for global warming in the US. They turned off the air conditioning, you know, and they scheduled it in July, so it'd be really hot and everyone would be sweating. It was sort of a great theatric effect. That's why Audrey scheduled my talk, you know, when she knew a badass storm was coming, and she knew this a month in advance. You know, this really cold day. I didn't get her to open all the windows though, for the opposite effect. But that's because we're not in the theatrics. But so his famous thing, and it's been in movies and everywhere since then, was that his office on the west side of Manhattan would be underwater in 40 years. This office will not be here, it will be underwater in 40 years. So just to get up to the curb at which his office sits, you need 10 feet of sea level rise. So he said this in 1988, 10 feet of sea level rise, which sticking with the metric system is 3 meters. So we are 88, we are 28 of those 40 years into it, and we've gotten 0.08 meters of sea level rise. So apparently the next 12 years are going to be rocking in Manhattan. And that's just to get to the curb. So things that people say, even, you know, this is the head of the US climate change effort, not our NASA guy, you know, just because they say it, just follow the data. And there's New York City sea level rise. So it's another one I have trouble seeing the rapid acceleration. I see sea level been rising throughout this century, again, at a roughly similar rate. What about extreme weather? So really recently, the temperature stopped rising meaningfully about 15 years ago. I always say, when I gave a talk for my daughter, my daughter's in college now, we've had no statistically significant warming since she was born. So global warming became climate change, you know, because the temperatures aren't cooperating. So we're going to talk about extreme weather. You know, we're messing with the atmosphere, and there's got to be way more storms and more intense storms, and that's what you hear about today, right? That's the main meme. So a professor at Oddball and many others, alumni here, Roger Pilkey Jr., great guy. He's a guy who's in the mainstream of climate change. It's a problem. We got to work to address it. He's on the IPCC board. He's not a skeptic or a lukewarmer like me. He's in the mainstream. But he gathered data on extreme weather and then ultimately decided, well, maybe we shouldn't go that direction. He is now a sports physiology medicine. He's been so attacked. They tried to fire him from CU. He's been attacked all across the country for the terrible crime of gathering empirical data and publishing it and presenting it to Congress. This is not his data. He's gathering data from governments and around the world. He is now in sports psychology. So obviously the most important change about weather is what do they mean to humans? So this is deaths per year from extreme weather. Floods are huge here. Floods are the biggest thing. Floods kill the most people. But there's floods, there's hurricanes, there's tornadoes, there's droughts. You know, and you go back early this century, half, third, 250,000 people a year died from extreme weather. It's a big planet. And of course, most of it's in poor countries. They have a flood and, you know, they're not prepared and they die. It's tragic. So here's the trend. If you look at red, it's correcting for population. So of course that's gone from, you know, 240, you could go way back here, we had quieter weather, you know, 80 to 5, 95% even from a quieter base. Reduction in the number of people dying. It has continued downwards. If this doesn't mean extreme weather disappeared, it means we've gotten better at handling it. So it's not a problem. In that debate I did on the moral case for fossil fuels, one of my opponents said, there's 35,000 people a year that die from extreme weather, and we have to take action on climate change. Now, she didn't know it used to be 10 times as great. I don't know what action she wants to take. But, so that's it. And so, not just to put it in economic terms, this is, as I said, global related disasters. Hurricane Katrina, think of Sandy, extreme weather. They flood, they destroy property, you have to rebuild it. So what is the trend of that as a percent of GDP? Obviously, if you go back 300 years ago, there weren't a lot of people with coastal houses in Miami, so the total dollar damage won't be that great. But when you add houses to the beach, so you've got to correct it for what's the size of the economy. And so this data is only 25 years, but the direction, like most of the directions, you're going to see downward, not upward. Forgetting the economics here, wealth and all that stuff, or even human responses to it, cyclone is the global name for hurricane. We call them hurricane, in the Pacific they call them typhoons, but they're all cyclones. So this is how many, I'll use the word hurricanes, have made landfall around the globe. And this data, we good data from 1970. And this is major hurricanes, and these are smaller hurricanes. You see any big increase, this increasing extreme weather? I don't either. This is just US, this is where we live, and here's a different way to present the data. This means it was 2,200 days since the last major Cat 3 and above hurricanes hit, when this one hit. So when these bars are short, that means it wasn't that long ago with a big hurricane, another hurricane hit another hurricane. So this is all about 80 major hurricanes that have hit landfall in the US since the start of this data, which I think is 1900. So these are all the major hurricanes that have hit the US. Look at the Wright bar. We are in right now the longest period without a major hurricane hitting the US in 115 years. And I should update this data. It's actually 4,000 days now. It's soon going to be twice as long since between major hurricane landfalls in the US in 115 years. So, and that could be random. I'm not saying extreme weather is going down, but it's very hard to look at any of this data and see it going up. What about tornadoes? It isn't hurricanes, it's got to be tornadoes. So this is F3, sort of a rating. It's like category 3 in hurricanes, or F3, F4, F5 are the giant tornadoes. It's the same thing for tornadoes. Just major tornadoes hitting in the United States. 90% of the tornadoes in the world are in the United States. Anybody see the big uptick in tornadoes and extreme weather? Me neither. What about flood damage in the US? Maybe the floods are just here and they're not in the world. That doesn't look like it's going up. Drought. There's very high quality graphics on this one. But red is the US and blue is North America. And a little story, you remember the Dust Bowl? We did have a period in the late 1930s or whatever, crazy droughts, they go down again. A lot of droughts again in the 50s, they go down again. And so that's drought in the US. It definitely, there's periods where it's bad and periods where it's not bad, but I'm not spotting the big upward trend. Raise your hand if you are. Here's the world. Different degrees of drought, right? Below average rainfall, way below average rainfall, hasn't rained in a long time. That's again, these data sets are different lengths. In every case, I've taken the complete data set. I've never cherry picked a time period. These are all complete data sets. But that's what we have good drought data over the last 30 years. I can't see the upward trend. Again, I could be blind. Here's one near and dear to my heart. This is snow cover in the northern hemisphere. So this is not just US, this is the top half of the globe. During wintertime, how much of the ground is covered with snow? Or not during wintertime, this is year round. So you can see in the summertime, there's less snow. Does that make the data make sense? In the peak of winter, there's more snow, and it melts again in the spring, and then it snows again. So this is data from 1972. So this is 45 years of data. So that's the whole northern hemisphere. Now you can definitely see variations, right? There's years with moisture and where the air masses are. There's more snowy than other years, and it changes. And I remember one of these very well. You can see this one. If you look at the maxes, this is the lowest one on the plot. This is the year my parents bought the condo in Breckenridge. And it wasn't just the northern hemisphere. It hit home right here. Breckenridge opened, I think on February 5th, and was open for 4 days in the entire ski season. 4 days in the 1981 ski season. So we didn't call it climate change then, but it really sucked because I finally had a place to stay where I could ski. I went to college the next year. So I've generally been a lucky guy, but I'm pissed about that year. And if it had gone down like this, like I think from the media, at least I'd have thought, well, it wasn't bad luck. It wasn't me, it was everybody. But I'm not seeing a strong trend there. Glaciers. So I'm also a mountain climber, as you guys know. So this one, there is a strong trend. There is a strong trend. Liz and I were married in Ecuador, and we're going to go climb down in Ecuador this summer and take our son up climbing. And I know for a fact the glaciers are going to be much smaller than they were when we climbed. And when we climbed in the late 80s and the early 90s, they were much smaller than the guidebooks we read written in the 50s and 60s. So glacier retreat is very real, particularly at the equators. But it started, 160, 170 years ago, and it's been dramatic long before the rise of CO2 emissions. A friend of mine, a climber, actually a friend of a friend, said a post today, he's climbing Mount Kenya and the glacier's disappearing, and God damn it, and Trump won't take action on climate change. Now, in the equators, I took out a plot, although I have it in the appendix if people are still bored. I showed the temperature change versus latitude. The southern hemisphere has warmed almost not at all. Almost all the warming's been in the northern hemisphere, and it's mostly been in the high latitudes. In the equator, the temperature's not moved at all. So when people tell me in Ecuador, which is right in the equator, and Kilimanjaro and Mount Kenya, and the Peruvian Andes, in Indonesia, Carten's Pyramid, these equatorial glaciers have contracted a lot, but the temperature hasn't changed. So people constantly blame that on climate change. Now, I do think it's human caused because of land use. As population has grown, you cut down trees, you cut down forests and grow crops, air becomes drier. To have glaciers at the equator, you gotta have a lot of snow up high where it's cold that accumulates and then it flows down into ablation zones where it melts. And so those places have become drier, and I think that's human, but nothing to do with CO2 emissions. But you will hear forever that the melting of these glaciers is driven by, your driving a car or fracking a well. But there's the glacier recession data. It is very real. It's been going on for a long time and long before CO2 emissions. But I personally believe, we don't know it for sure, I personally believe it is a large part humans, both by making these places drier by removing forests, and also when you build stuff and you construct stuff and you farm, you create dust, and when you spread dirt onto snow, it melts a lot faster. So the reason the northern hemisphere is warmed, southern hemisphere hasn't changed a lot, the human impact is bigger. The population centers, industries in the northern hemisphere. So is there a dust impact on melting glaciers? Probably. Is there a moisture content in glaciers? I think so. So on CO2, the other thing to think about CO2, I mentioned at the beginning, it's plant food. When you have a greenhouse, you jack up the CO2 concentration to far higher than we live in right now because plants grow faster. Again, everyone knows that. It's not controversial. It's more plant food. No one talks about it anymore. But here's a new area of study. And there are a lot of different people working on it. It's very cool. I remember when I was a kid. So in this, we're running out of resources. One of the other big things we heard was desertification. The Sahara Desert is growing. It put in me, I've been to Africa a few times. I went when I was young, or relatively young. I was in college to see it, because my passion's been poverty. But the Sahara Desert was growing further south. And then you can't grow anything there. And there's this region right below the Sahara called the Sahel. So it's dry. It's like Wyoming. It's dry, but there's rains and you can grow some stuff, but it's quite variable. It's quite marginal. This is the Sahel. So what's happened in the Sahel is it's become massively more productive. You can grow crops again. It's a little bit wetter, and there's a lot more plant food in the air. So this is the whole globe taking the annual productivity. So this is not just crops. This is rainforest, grasslands. It's not just man-made stuff. It's just